Hello everyone. In unit number 2 mass transfer, we are going to learn mass transfer in bioreactors in this video lecture. So let's look at what we are going to learn, what is our learning objective. So we will first illustrate the process how oxygen is taken up by the microbes which is growing in submerged fermenter. That's an aerobic fermentation process. We'll also see oxygen transfer rate termed as OTR and oxygen uptake rate termed as OUR, and we'll relate them under steady state condition and how they are influencing the fermentation process. We will find out methods by which you can experimentally and theoretically use it to find KLa values, oxygen transfer coefficients, to the water fermenting liquid, how it is related and how it can be calculated. That also we'll see it in this video lecture. So first let us take up the topic on oxygen uptake in a fermenter, that is aerobic fermentation process. Aerobic fermenter has a mixing unit, an impeller, and also a sparger is present. The sparger provides supply or supplies the air to the fermenting liquid. Oxygen is necessary for microbes that is growing inside this liquid broth. The air which is present, it has got 21 mole percent of oxygen, but it is in the gaseous phase. Now that oxygen should dissolve in the liquid and then it should be available to the microbe for reaction process. Now the solubility of oxygen in water is very low, whereas nitrogen which is present in the air here, it is not that much soluble as much as oxygen, but oxygen is the one which is necessary. And the oxygen transfer has got different rates that is present over here, different resistances are present. So our focus is mainly on the KLa values, the transfer of oxygen from air to water. Now we'll analyze how it can be done or how these resistances affect the entire process. You should note that there is something called DO, dissolved oxygen probe, a sensor that measures dissolved oxygen in the liquid. You have pH sensors, carbon dioxide sensors, pressure sensor, different sensors are there, but you should be aware that there is something called as DO, dissolved oxygen probe. Probe is nothing but a sensor which is used for measuring the oxygen concentration in the liquid. The gas which is coming out here, it escapes over the vent, that is exit gas is going out, and the sparger which is present, based on its design, it produces bubbles of various size. The sizes may be very small depending upon the orifice size of the sparger. The size of the bubble will be very small at the bottom, and as it moves up, it's called as residence time, the time required for the bubble to reside inside and escapes. The time lapse over here for each bubble depends upon the size of the bubble. Smaller the bubble, slowly it goes up. It depends on the sparger. But if the size is very small, it will be having very high pressure. You may require high pressure for operation. The flow rate maintenance will be difficult. If the bubble is of larger size, then it will go quickly. That is one part. Second thing is, as the bubble size is larger, the surface area, that is bubbles outer surface area is available for the mass transfer. The overall surface area will be less. We call it as volumetric surface area. The volumetric for a given volume of air, the surface area available for the mass transfer with the liquid will be small or will be less when you have a bigger bubble. So it is always ideal to have small bubble so that it resides for a longer duration. Also, it will provide more surface area for the mass transfer. That is the issue with the gas bubble size. Then another issue that we will come across here is the solubility. Oxygen is sparingly soluble in liquid or any liquid solution, specifically water. And you should know that this is not pure water or just water. You have other nutrients here, glucose, proteins, other nutrients are there. So this may not behave like a Newtonian fluid. It may behave like a non-Newtonian fluid. And to avoid cluttering of molecules here and there, that is to maintain a uniform concentration of all the molecule, we are using the impeller. Impeller is nothing but a mixer which mixes the entire content including the oxygen. So there is a uniformity in all quantities or nutrients that are available. So let us focus mainly on this particular interface of gas to liquid. So we see that one gas bubble, let us take it, and one microbial cell, let us consider how the oxygen from the bulk of the air molecule move inside the microbial cell and undergoes the reaction. So we are tracing one oxygen molecule here. So it takes this particular path as a representative path, which is listed as 7 steps. You have the air bubble, the dark gray color air bubble, and surrounding this there is a film, gray colored liquid film, because air is a gaseous molecule. Surrounding it there is a liquid, bulk liquid. So obviously there is a small thin film produced outside the air bubble. And here the gray color, dark gray color, is the microbial cell. It is a solid surface. Nearer to the solid surface there is a thin liquid film generated. So these are the two films that we will be considering. Now, the first path, that is bulk gas phase in bubble. Oxygen flows from bulk of the gas nearer to the surface. Second step is gas liquid interface. So here there is a gas liquid interface, this interface outside the gas molecule. So in the first step it will go nearer to the interface here. Since it is within the gas and movement is Brownian movement, there is no much resistance in the step 1. There is no much resistance at all for the oxygen to move to nearer to its boundary. Near the boundary, it has to transmit, the second step, it has to transmit from gaseous phase to liquid phase. Thin liquid film is there here, so it has to transfer. So this transport also not much difficult. But the third one, the liquid film around the bubble, that is from the liquid film to the bulk, it has to flow. Third step, this is very critical. This is the one which is having the highest resistance to the mass transfer. So the KLA, what we are going to measure, that is on the liquid side, will be more because of this one. That is the resistance we'll have to focus upon this one. This is the most resistant step. The oxygen molecule which is dissolved in here, it has to come to the bulk of the liquid, the outside, in between these two films here, the entire liquid which is present, this is the bulk of the liquid. In the bulk of the liquid, since there is a mixing, constant mixing by the stirrer, this bulk of the liquid is continuously mixed. So the transfer of oxygen from here nearer to the outer surface to nearer to the outer surface of the cell, it will be quick. The step number 4 is very fast because of outside mixing, external mixing. So the resistance offered in the step number 4 is also very low. Step number 5, from the bulk to the nearest liquid film, the oxygen should enter, that is, it should diffuse. So this is also quick enough. It depends upon the layer that is present. Slight amount of, you can say, it is the next level of resistance compared to third one. Third step is the highest resistance, fifth is the next one. The reason here is oxygen, the air bubble which is coming here, the oxygen which is dissolved, molecular point of view, it is slightly comparable with this film because microbes are of very small size, not observable to the naked eye. Whereas this gas bubble, you can observe it, you can see it, it's a macroscopic. Whereas this is microscopic. Even though the picture shown is big here, but in reality, in a realistic sense, this is macroscopic, and you can see this one. Whereas microbial cell, you cannot see even this layer is also invisible to you. So within this thin layer, very thin layer, the air has to, the oxygen has to transfer. In fact, even though there is a resistance, still we can neglect to some extent. Then there is a transmembrane transfer of oxygen across the membrane. So cell membrane, oxygen has to transfer inside. This is quick because of passive transport or active transport, a mechanism available with the bacterial or microbial cell. Because it requires oxygen, it senses it as an important element and it takes it in quickly. From the interior cytoplasm to the reaction site where the reaction is taking place, the oxygen has to move. That is the seventh step. So from 1 to 7th step, the important one is third step, where the oxygen is transferring from the film outside the gas bubble to the bulk of the liquid. So this is the most important step. This is the case when you have a unicellular system. If there is a flock, multicellular system, flock means solids, debris are there. So that may add up an extra resistance in that case. Usually in fermentation cases, we consider, most of the time, we consider it as unicellular system. Now, the oxygen transfer rate. The next step is oxygen transfer rate. So the resistance path we have seen, the gas bubble to the bulk of the liquid. So the transfer of oxygen from the gas bubble to the bulk of the liquid is called as OTR, oxygen transfer rate. Nothing but the how much mass transfer is taking place in reality. So the equilibrium concentration, the oxygen solubility in the broth is Ca star L, which you have seen in the previous lecture. Equilibrium composition Ca star L is oxygen solubility in broth. It depends on the broth condition, temperature, its pH, many parameters are there. Inside the gas, the concentration of oxygen is very large. You can see the concentration profile drawn here. In the gas phase, it's very large, high concentration. At the interface, it drops very quickly, very sharp decreases there because of the large amount of resistance. So also the solubility is very low. In the bulk of the liquid, it slowly reduces, and at the interface of the solid and the liquid, slightly decreases, and this decrease is slightly comparably negligible. Compared to this decrease concentration is negligible. The microbe, it has to do some undergo some aerobic reaction. That means it requires oxygen for its survival or some metabolic reactions. It has a capacity to take up, that is called as oxygen uptake rate. The oxygen that is available to its nearest surrounding, it is taken inside the reaction cell and it is undergoing a reaction here. So that particular rate at which oxygen is supplied over here is the oxygen uptake rate, OUR. Now let us relate this and this, that is OTR and OUR. Let us relate it. So OTR from the mass transfer concept, that is convective mass transfer concept, the major resistance to mass transfer lies over here. This is the point where KLA is the important mass transfer coefficient that we have to consider, because KLA is very less compared to KGA. There is no resistance here at all. That means KGA is very very large. When the KGA is very very large, overall mass transfer coefficient what we had written earlier, capital KLA, we can rewrite it as small KLA, because your KGA, gas phase mass transfer coefficient, is very high, and KLA will be the overall mass transfer coefficient will be almost same as liquid phase mass transfer coefficient. So this hence we are replacing with the KLA, and the relation, that is equilibrium composition minus bulk phase concentration. Equilibrium composition over here near the film and bulk concentration. So these two differences will take it up, that is OTR, oxygen transfer rate. Now OUR, it depends upon the quantity, how much it can individual cell can take, multiplied by what is the biomass. This is Q naught. The Q naught is one cell how much can take. I mean 1 gram of the cell how much it can take. X is nothing but the total quantity of cell that is present. So in the entire reactor we have to consider X quantity of cell is present in 1 liter of the fermentation liquid. So total oxygen consumed by entire volume, it's called as volumetric consumption. Volumetric consumption of oxygen by the microbe is this Q naught, that is oxygen uptake rate. In one volume of the bioreactor, total biomass is present. All the biomass put together, how much oxygen it is able to consume, that is oxygen uptake rate. Analogously, if I take some example, say, let me say that in the class there are 5 students. Each one has a capacity of taking up apple and do some work. Okay, so the capacity of each person is this Q naught, small Q naught is 2. 2 apple each person can consume, and there are 5 students. That means you require 5 into 2, 10 apples for performing one work. Now imagine this is the requirement. OUR is the requirement. 10 apple is the requirement. Now say that OTR. So this much quantity. How much I have here? I have say 100 apples with me. So giving the 10 apple is not a big deal. I can easily give it to you. So the mass transfer resistance, or the from the giving point of view, there is not a problem. The problem is with the capacity itself. So system itself, the biomass itself has a problem of consuming it. That is fine. That is required. That is the essential thing. You should provide as much as possible. On the other hand, let me say this KLA is related to my capacity to buy, purchase power, or let me say I don't have sufficient money. I have only 5 apple. I don't have more apple. I have only 5 apple. So in that case, what I will do, I will give only 5 apple. Even though you have the capacity to take total 10 apple, you are provided with the 5 apple. So what you will do, you will, there are multiple possibilities. one of the possibilities that each one of you share properly equally. So even though you want two apple, you will take one apple each. 5%, 5 apple. So so you are starved. That means instead of 10 apple, you are getting only 5 apple. You are starved, right? Another possibility is there that one person, some people will take two apple. So two people will take full two apple, and one person will get one apple. Another two student will not get any apple. So some cells may not get the oxygen, some cells may get the oxygen. That is the improper distribution, non-uniform distribution, right? So this is the dangerous situation. This KLA or the power of purchasing is less, right? Since this KLA is less, oxygen transfer rate is also less. That will hamper the growth of the microbe. So our main target is this KLA. So first we'll focus upon this part, that is how much X is required, how much X we can grow. Then we'll focus upon KLA, how we can improve it, the impact of KLA on biomass growth. So let us consider the steady state condition. Under steady state condition, whatever oxygen is transferred, the entire thing is at the same rate oxygen is taken up. Okay, uptake and transfer both are equal under steady state. So your KLA CL star minus CA, this is the mass transfer equation, will be equal to Q naught X. Now this is C star oxygen solubility. It is dependent on the temperature. I have given you one table here. This table is from um, Perry and Green, that is Perry's Handbook of Chemical Engineering, which I had mentioned to you in the previous topic earlier video, where I told you about a data handbook can be used to obtain certain information when the experimental data is not available. Now I want the solubility of oxygen at different temperatures. You can see it here. It's in kg per meter cube. Oxygen solubility, which is nothing but C star. This value, C star of solubility limit. It is for the pure water at 1 atmosphere. Note that 10 power minus 3 kg per meter cube, this unit 10 power minus 3 kg per meter cube is same as 1 ppm. So at around room temperature, somewhere around here, if you observe, it is somewhere about 8 ppm, roughly around 8 ppm, that is 30 degree, it's around 8 ppm, right? So 8 ppm is equivalent to 0.00045 mole percent if you convert it. 1 ppm is equal to 1 mg per liter. So if you convert the value, it becomes around 0.00045 mole percent. But in the air, oxygen is present at 21 mole percent. Look at the difference here. So maximum it can dissolve is this much percentage in water. That's the capacity, ultimate limit of C star. For a different type of the liquid, it will be different. It's only for pure water. You change the liquid type, this value will change. C star will change. You can improve it. That's possible. First, let us identify under the given condition what is the maximum biomass we can grow. If the biomass has to be maximum, all available oxygen in the bulk nearer to the surrounding of the cell, oxygen which is present, all have to be consumed. What it means is the dissolved oxygen or the CAL, the bulk oxygen concentration CAL, which is nothing but the dissolved oxygen nearer to the cells in the bulk, is zero. There is no oxygen at all. Means as soon as the oxygen is transferred there, all the oxygen is consumed. When all the oxygen is consumed, more than that is cannot be consumed, right? So that means biomass, whatever is produced at that level, is a maximum possible value. So we can calculate X max using this equation. So the X max you can calculate when CAL goes zero. So I can rewrite this equation. X max is equal to KLA into C star divided by Q naught. This is the equation. So you can calculate X max given your system. Now, it may so happen that KLA is very low. This KLA value is very low. What will happen? If KLA is very low in the fermentation broth, oxygen is limited by mass transfer. The amount of oxygen that is present will be limited by the mass transfer because of KLA. KLA is the resistance offered to the mass transfer there. So cells may be starved of O2. Oxygen may not be sufficiently available. So you have to increase the KLA value. Now, if you think that your required concentration of X is less than X max, maximum is, say, let me say it is 12 gram per liter. Maximum 12 gram per liter you can produce or grow in the fermentation medium. And your required concentration of biomass is 10 gram per liter. That means maximum is 12, required is 10. Fine, you can grow with that. Now you may have to increase the KLA value. If required is less than X max value, you may have to increase the KLA. So you can estimate whether KLA has to be increased sufficient Whether mass transfer is present or not, you can identify. So related to it, I have a problem here, numerical. So it goes like this. A strain of Acetobacter vanillandii is cultured in a 15 meter cube of stirred fermenter for production of alginate. That is one key sentence. Three data are given. KLa value given. Oxygen solubility, C star, equilibrium composite concentration, that is solubility limit of oxygen under this condition is provided. Specific oxygen uptake rate is also provided, Q naught. You have to find out maximum cell biomass that can be produced, Q naught. So, sorry, given the Q naught value. So, Q naught I will convert it because it is given in per hour and KLA is in per second. Also, it is in gram and this is in kg. So, let us convert certain units there so that we relate them equivalently. So, I'll convert oxygen to kg because oxygen is written in kg here, and biomass let me convert it to gram because normally biomass concentration required is in terms of gram only. Time is second. Please note this kg and gram both are there. I have not converted this biomass to kg. I kept it as gram only. So the meaning of specific oxygen uptake rate meaning is how much oxygen can be taken up by 1 gram of the biomass in 1 hour time. In other words, here if you see it converted value in 1 second, 1 gram of the biomass can take 1.11 into 10 power minus 7 kg of oxygen. That is the meaning of specific oxygen uptake. The way I told you, 2 apple can be taken up by one student, right? So using that equation, X max is equal to KL C star by Q naught. If you use this equation, it used to be 12.3 gram per liter. Now there is another situation, that is modification of this situation. If a copper sulfate is accidentally added, some copper sulfate has fallen into the fermentation broth, right? It will reduce the oxygen uptake rate because it will consume oxygen. Oxygen uptake rate is reduced by the microbes. So instead of 12.5, the new value is 3 millimole per gram per hour. Instead of 12.5, it is 3 now. What would be the maximum cell density in such case? In this case, what will be the X max? That's what you have to find out. It's simple. Rewrite this equation means recalculate the whole problem. Instead of 12.5, substitute 3. That's it. Redo the problem. So this gives you 51.25 gram per liter. In this case, X max will be 51.25 gram per liter. It is something very similar to saying your capacity. I said 2 apple, right? If by chance some I made some mechanism so that your requirement of apple is not 2, it is 1 now. So if I give 5 apple, it will be self sufficient. It's very similar to that. So you can do your perform the proper work. So now the next one is to determine this oxygen transfer coefficient KLA. So we understand that KLA is very important in the which is a mass transfer limitation in oxygen transfer. How do we estimate it? So there are three different experimental method which I'm going to explain now and one theoretical method. Experimental method is oxygen balance method. It's also known as a static method. Another one is dynamic gassing out method. It's a dynamic gassing out method. Third one is sulfide oxidation method, a titrimetric method. Theoretically, we have empirical equations which can be used under certain conditions. Let us look at the first one, oxygen balance method. The concept is very simple here. You have a fermenter, let the reaction go on, fermentation let it go on. You supply the air. It's a realistic situation, right? It's a realistic situation, and in fact, it's a more reliable but difficult to perform. You require more high level instrumentation for this. Errors are very less in this. So what you do is air will be flowing in, air will be flowing in, and it will go exit. Meanwhile, what will happen? Oxygen will be transferred. How do I note? How do I identify oxygen is transferred here? Identify the concentration of oxygen in the air which is coming in. Identify the concentration of oxygen that is going out. Take a difference between these two. The rate of oxygen supplied minus rate of oxygen exiting. Something should have been absorbed here, right? So the difference between these two should be the oxygen transfer rate Na. So you have to make use of instrument to identify oxygen concentration because the difference is very small Very accurate concentration difference has to be required. So we will be using mass spectrometry. Real time mass spectrometry can be used for these two things. So ordinary instruments are insufficient. You require high end instrumentation for this. Mass spectroscopy is very costly. So that gives you very accurate result of oxygen transfer rate. Next, we require KLA. When you calculate KLA, two things are there. That is this oxygen uptake rate over here. Even though I written Na here, it is oxygen uptake rate only. Right? I mean transfer rate. Sorry, oxygen transfer rate. So the oxygen transfer rate Na divided by C star minus CAL. C star is the equilibrium composition, which I can identify from the data handbook. But actual concentration in the bulk, oxygen concentration in the bulk I want. So for that, dissolved oxygen sensors are used. So the DO sensor gives you real-time reading of C value. So given the differences between the two and C value here and C star from the data book, you can calculate KLA. So this is one reliable method, but it takes more instrumentation and values. So dynamic gassing out method is another method. Dynamic gassing out method is another method. It's an unsteady state measurement uh, where uh, where you are going to allow the air into the fermentation liquid, which is real time. In fact, it's a real time. So allow the air to flow at one particular time. As a function of time, at one particular time you are going to shut down the supply of air. It will the You have a dissolved oxygen sensor in your system. In the fermentation broth, dissolved oxygen sensor is present. That dissolved oxygen sensor will record the concentration as a function of time. At a t0, you will stop it. So it will go down. See, because microbes are there, microbes will be consuming the oxygen. Microbes are present, it will be consuming the oxygen, but there is no input, no supply of oxygen. But the bulk liquid, it already has lot of oxygen available there in the beginning. That gets consumed, but there is no input. That means the concentration in the bulk liquid keeps decreasing. That keeps decreasing. At a one particular time interval, you will switch on the air. This particular point where you switch on the air should be above the critical concentration. Its critical concentration is the minimum oxygen concentration required in the bulk so that the biomass can grow or biomass can survive. If biomass dies, you cannot do any experiment, you cannot do any fermentation. It should be alive. If the biomass has to be alive, C critical value should be maintained. So this particular point is always above the critical value. So at this critical value, you switch on the air and dissolved oxygen concentration keeps increasing and it will reach the final value. The final value, let me call it as C bar AL. In between, I can record the values as a function of time. So at two different time intervals, T1 and T2, I found CAL1, CAL2. So given these five data, C bar, CAL1, CAL1, 2, T1, T2, using this formula, ln of differences between the concentrations by T2 minus T1, I can find out KLA. This is reliable method, but it requires instrument like a DO and on off carefully you have to do it. So it's more reliable. It's realistic experimental method. If one data point is insufficient, if you observe it carefully, it is in the form of numerator is y, denominator is x, and this is the slope of the line. So what you can do is you can find out many points here, maybe around 8 to 10 points on this line corresponding to T1 and CL1. Use this equation and calculate around 5 to 6 set of values for numerator and denominator. So plot them. This is the numerator and T2 minus denominator is the x-axis, numerator is y-axis. Plot a graph y versus x. It will be a straight line passing through origin. The slope of that will be KLA. So that is the averaging, more reliable value for the entire zone. So this is the second method. Third method is sulfite oxidation method. It's a titration based method, cost effective but not reliable. Here in this case, it is not a actual condition experiment. You'll be sampling it. So broth will be there, but the biomass which is growing, it is not there. It is just the broth which is present. You will add sodium sulfite along with the copper and allow the oxygen transfer. You will take sample for some time interval of time. You'll do that complete what you call supply of oxygen. Say for example 5 minute or 10 minute you'll supply the oxygen. At the end of that you collect the sample and titrate it again at sodium thiosulfate and in presence of iodine. Iodine gives you the color change. So that will the change from the beginning zeroth time to the 10th minute, the difference in sodium sulfite concentration gives you the how much oxygen is consumed. You can see that 1 mole of oxygen consumes half mole of 1 mole of sodium sulfite consumes half mole of oxygen. So if you know the concentration, how much concentration of sodium sulfite is consumed, 0th time to 10th minute. So that much of oxygen is consumed, dissolved, all right? So we assume here that in the beginning, initial concentration, that is dissolved oxygen concentration is zero. Initial concentration is zero. This is the assumption which makes it more not reliable. So this value is always higher than the previous two methods. The KLA that you measure here, it's always higher than dynamic gassing out method and static method. Oxygen transfer rate, the transfer rate that you calculate here will be equal to CKLA into CA star. So the CA is equal to 0. We will assume this. CA star from the data book, KLA you can measure. This OTR you obtain from the difference in sulfite concentration between two time intervals and equate it with the oxygen, how much oxygen is consumed per volume of the reactor. So this is third method. These are all experimental methods. The last one is an empirical method. If you observe here, there is one equation for KLA. So this KLA is given with one equation P by V U power P by V power 0.7 V U power zero point 0.2. P by V is nothing but power dissipated by stirrer to the liquid. So there is agitation. Agitation supplies power. Broth volume, the liquid volume. This is called as power to volume ratio. P by V. So this P by V is it can be calculated for a given condition. U is superficial gas velocity, nothing but what is the volumetric gas flow rate of air, you find out, divided by cross sectional area of the fermenter. So that gives you the velocity of oxygen that is moving upward. So that velocity, this particular equation, what it is shown, it is for a particular situation, for a particular set of volume of the fermenter and set of P by V values or U values. For different region, a different equation will be there, but overall it will be same P by V U. But this powers 0.7, zero point 0.2 and this constant may slightly differ, but it is remain almost same for all situations. The overall equation strategy, these are called empirical equation. It gives you a rough estimate when experimental methods are not available, but they are not much reliable because it may change over the situation, like non-Newtonian fluids or the sparger designs, bubble size, nothing is considered in this. So when you change that, the value still it may remain the same because P by V or U is not changed. All right, so that way it is not that much reliable. So we have come across four different methods to estimate KLA. To summarize this lecture, we have learned mass transfer application in bioreactors, that is oxygen, how it is taken up in the submerged fermenter. We also seen OTR and OUR, how are they related, and we have seen that KLA estimation is very important. So we have seen three experimental method and one empirical method to determine the oxygen transfer coefficient KLA. That's it for this lecture. Thank you.